Okay, this is the last example problem of this ES206 fluid mechanics class. Unit F2, page 9. Let's take a look. Oh, before we do this example, let's take a look at the video on the previous page. So this is a video. Here's an example of water fountain. It's a simple pipe system design. Incoming flow turn 90 degrees and another 90 degrees. And then this is a branch flow, reduced cross section, water gets out. Okay. Alright, so water flows steadily through this 0.75 inch diameter galvanized iron pipe system, as I showed you in the video. Okay. Flow rate is given. Flow rate Q is 0.02 CFS. This is a cubic feet per second. Okay. Now, here's a situation that you are an engineer. This is probably your very first job, designing this system. Okay. So you made a decision. One of the decisions you made was you chose 90 degrees threaded elbow here, and another 90 degrees threaded elbow here to turn the flow 90 degrees and twice. And then connect it to the branch flow T, and then one side of the T is connected to across the ball valve. In other words, this is always closed. So the flow goes up, and then you decided to reduce the cross section a little bit, then you come up with the water right here. Okay. So now you work for your boss. Usually your boss is not necessarily engineering person. So your boss may be focused too much on cutting the cost. So having said that, your boss said this. Your boss suggested that friction losses in the straight pipe sections, okay, are negligible. Okay. Compared to losses in the threaded elbows and fittings of the system. Essentially, your boss is saying the loss associated with this pipe, that pipe, those pipe are very small compared against those fittings and turning elbows. Then basically, hey, let's forget about it. Okay? Do you agree or disagree with your boss? Support your answer with appropriate calculations. Agree or disagree? That what really means that is your boss is willing to cut the cost. So let's say he's choosing very cheap material. It looks like 0.75 inch diameter galvanized iron pipe. Very cheap pipe. You know, it's basically extremely rough internal surface. But he keeps saying, well, you know, you don't have to worry about that kind of loss, because most of the loss comes with this and this and this and that. Do you agree or disagree? Okay, let's just take a look at actual calculation. Then based on the numbers you got, you can agree or disagree. So what you need to do is recognizing that head loss, total head loss is major head loss and minor head loss added together. Okay? So your boss is saying this is the big one. And forget about this. Okay? This is a major head loss of the pipe itself. Minor head loss is a loss associated with minor components. Such as 90 degrees elbow, fittings, branch T, reducer, those kind of components. Is that really true? It depends, really. But why your boss is arguing, hey, this is nothing, this is the main thing, the reason here is he probably wants to use very, very cheap material here, emphasizing that even though I'm using galvanized iron pipe, still this is nothing. Don't worry about it. Okay? So I guess the right thing to do is, let's compute those. Okay? So I'm going to start with major loss. Major loss with using galvanized iron pipe. Okay. Even if you're using pretty cheap and rough pipe, this loss is still small and you can ignore. Well, wait a minute, I begin to feel really funny. Is it really true, or is that just an argument based on the feeling? Okay? So, major head loss. As you know, this depends on the friction factor, length of the pipe, diameter of the pipe, velocity squared over 2g. Length of the pipe itself, let's go back here, consists of this 6-inch length, another 6-inch length, this is 4-inch, and then one more. So 6 plus 6 plus 4 plus 1. So let's just add them all together. 6 plus 6 plus 4 plus 1 inch. Total 17 inch. This is the total length of the pipe. Galvanized iron pipe. Okay. Diameter is 0.75 inch. Okay. Let's find out the flow rate. Actually, not the flow rate. Average velocity within this pipe. This is Q over A. Okay. So since flow rate is already given, flow rate is 0.02 cubic feet per second. Cross-section area of the pipe is cos pi over 4. 0.75 divided by 12, making it feet. This thing square. Okay. So the average velocity within the pipe you can determine 6.519 feet per second. Based on this average velocity, I want to compute the Reynolds number, trying to see if this is laminar or turbulent. Let's determine Reynolds number based on this average velocity you just found, and diameter, and kinematic viscosity of water. 6.519 feet per second multiplied by diameter is, once again, 0.75 inch divided by 12, make it feet. Kinematic viscosity of water is 1.21 times 10 to the minus 5 feet squared per second. Make sure you need to look up your own property table, which is handout. Confirm this property. Kinematic viscosity of water. You determine Reynolds number, which is 3.37 times 10 to the 4. This is bigger than 4,000. Actually, flow is laminar. Oh, okay. It's not. Flow is not laminar. Flow is not laminar. Flow is turbulent. Sorry. Flow is turbulent. It's high Reynolds number flow, more than 4,000. Okay. If the flow is turbulent, of course, the friction factor here depends on two things. Number one depends on Reynolds number. The other one depends on how rough your pipe is. Oh, I haven't even, my butt feeling starts to grow. Okay, so he is saying this is a small tiny rust. I'm going to choose the pipe which is cheap and rough, which is galvanized iron. Galvanized iron is pretty rough pipe. How rough it is, let's find out. Okay, in order to determine roughness, I'm going to go back to page 2 of the note. Epsilon over D is something called relative roughness. In order to determine epsilon over D, you need two things. One is equivalent roughness, which is a height. Galvanized iron pipe is pretty rough pipe. Now, pretty rough pipe combined with small tiny diameter of the pipe make this even worse. Okay? So, what is the relative roughness? Epsilon over D. As I can see, epsilon galvanized iron is 0.0005 feet. Diameter of the pipe is only 0.75 inch. Oh, it's not that big pipe. So rough surface and smaller cross section make it really rough pipe. Okay. So this is relative roughness 8 times 10 to the minus 3. In other words, 0.008. Oh. Fairly rough pipe. So what I'm going to do is, using this information and this information, determine friction factor. How do you do that? I'm going to take a look at the Moody chart. Let's look at the Moody chart here. Okay. So this Moody chart tells you if the Reynolds number is 3.37 times 10 to the 4th, which is, this is 2, this is 3, so around here. So that's the Reynolds number. And then roughness, relative roughness is 0.008, which is here. Around here. Is that right? So around here, this is the, so that's where this 0.008 meet up with 3.37 times 10 to 4 Reynolds number. I would say friction factor 0.038. Okay, make sure you can do the same thing and find out friction factor out of Moody chart. Okay. So this is the friction factor I found. 0.038. Okay. So my conclusion is, move on. So major head loss is not so insignificant in this case, fairly big value. Let's find out. Friction factor we found was 0.038. Length of the pipe 17 inch, and diameter is 0.75 inch. Now, even though I don't want to use inches, this is just a ratio, so you don't have to worry about converting into feet. B squared over 2G. B squared 2G I just leave it as is. So my conclusion, major head loss, 0.861 times b squared over 2g. So this is intermediate conclusion. Even though your boss says major loss is nothing, this is how much major loss you have. Okay. So now we're moving on to the next step. Okay, let's find out minor loss. Minor loss, as your boss indicates, this could be fairly big portion of the entire loss of the system. Okay. Remember, this is, you're going to take summation of all loss coefficient for each minor device multiplied by b squared over 2g. Okay. So I'm going to go back once again to the figure, identify minor components. Each one of them is associated with minor loss coefficient. So this is a 90 degrees turning elbow threaded. This is another 90 degrees turning elbow threaded. So 2 times 90 degrees threaded elbows. Right here is a branch flow T. This is called branch flow T. This end is closed, so you don't have to worry about this one. But you have to worry about the loss associated with this branch flow T. And right here, cross section is reduced from 0.75 to 0.6. So you have 1, 2, 3, 4 devices. Okay? Four devices. 90 degrees elbow. Standard and threaded. You have another 90 degrees elbow. You have a branch T. You have reduced cross section. I'm going to take a look at one by one. This 1 and 2, the same thing, 90 degrees elbow threaded. Let's take a look at page 8. So this is a elbow, regular 90 degrees threaded elbow. KL is 1.5. So KL is 1.5. Another 1.5. Okay? Branch T. Let's take a look at the same page. So here's a different kind of T. Line flow, this is called line flow. This is called branch flow. Obviously, we have a branch flow T. It's a threaded branch flow. 2.0. So this one gives you KL is equal to 2.0. This one, well, we have to really estimate if you reduce the cross section 0.75 inch diameter to 0.6 inch diameter. Okay? So how do we do that? I'm going to go back one more page. So this is the case that if you connect the two pipes with a different cross section. This is a connection of a larger cross section pipe to a smaller cross section pipe, which is kind of similar to what we have reduced cross section. Okay. Now, if this kind of thing happens, we are going to first take a look at the ratio A2 over A1. So let's take a look at that. Ratio A2 over A1. this is really ratio of the diameter d2 to d1 squared. If this is a circular cross-section, because circular cross-section area is pi over 4 diameter squared, right? Pi over 4 cancels out. So cross-section area ratio is essentially diameter ratio. So let's just plug in 0.6 and 0.75 and take a square. And this is going to be 0.64. Okay, so this is area ratio 0.64. Let's go back to the plot once again. If you have a ratio A2 over A1 0.64 around here, you can read off the data KL. KL is, it's kind of tough. But I would say about 0.15. So KL 0.15. Okay. So what do you need to do? You are going to add these all together. Okay? Therefore, minor head loss is 1.5 plus 1.5 plus 2.0 plus 0.15 multiplied by b squared over 2g. So conclusion, HL minor head loss will become 5.15 b squared over 2g. Now I purposefully left b squared over 2g for both because those are the same thing. Okay, so here's the argument. What is the percentage of major loss and what is the percentage of minor loss, knowing that total head loss is addition for those? Okay, so let's find out percent major loss, which is 0.861 divided by 0.861 plus 5.15. This is going to give you percent major loss, which is 14.3%. Percent minor loss, it's the opposite of it. Obviously, 100 minus this, it's 85.7%. Okay, so you need those numbers. So your boss is essentially saying that ignore about 15% of the loss, it is nothing. Then I guess your response is, I don't think so. Do you say 15% insignificant and you can ignore? I don't think so. If this is probably, let's say, less than 5%, I agree. But this is not negligibly small body. I'm sorry. So that's my opinion, based on the numbers. Okay? So oftentimes we may encounter this situation, your boss basically trying to argue based on some kind of feeling. I guess the motivation behind it is trying to minimize the cost involved. Now you engineers sometimes may say, no, I disagree. But whenever you say that, you need to have a number backing you up. So this is a number. So I would probably ask this question again to my boss, saying, hey boss, this is exactly what you're saying. Major loss is actually 15% of the total loss. So these are the fairly significant component of the loss. Are you saying to ignore this. Okay? That may change your boss's mind. Okay? So this is the very last example program of ES206 fluid mechanics. I hope you enjoyed the video series.